Welcome everyone to the first session of the day, Learning in Humans and Machines from Optimizing Our Biology to Colluding with AIs. We're joined today by Surya Ganguli, Associate Professor at Stanford University, and Wendi Zhang, Business Development Partner at Gradient Ventures. Thank you, Surya and Wendi, for joining us, and I'm looking forward to the session.
Thanks.
Well, hello, everyone. Thank you for joining us. I remember 2 years ago at the MIT AI conference, my favorite talk was actually Professor Surya Ganguly's talk. And when I got asked to moderate this session, I was like, oh, yes, of course. So really excited to be here and hear, Surya, what you've been up to. So actually, why don't I just kick off with that? You know, what have you been up to lately?
Oh, thanks, Wendy. Thanks for the enthusiasm, Wendy. Yeah, we've been up to a ton of stuff. Like in general, I work in sort of neuroscience, machine learning, and physics. Actually went to MIT as an undergrad to study AI. Back then, it wasn't that interesting. It was like old school problems and expert systems and stuff like that. I kind of lost interest, went to Berkeley to do physics, did a PhD in string theory. Then I went to as a postdoc, I did neuroscience, and then as an associate professor, I started doing machine learning and so forth. So we've been working generally on like understanding how artificial neural networks work, applying machine learning to real world problems, and also understanding how biological networks work and trying to create next generation AI systems inspired by biology, basically. So that's kind of the overview of what we've been doing.
I love how each of these topics are very complex, and like a typical MIT grad, you're not just dabbling in the physics of things or the biology of things or neuroscience, it's everything combined. So actually, I'm curious to hear like this concept of neurobiology of the mind. It has always been interesting to me. For me, I grew up in a household where my dad is a professor of neuroscience. But to be honest, like I never really engaged a lot of conversations with him on that. I see a lot of these like pictures of memory cells and everything. But I've always been fascinated by it, just naturally gravitated toward that. So I'd love to hear from you. What insights can the neurobiology of the mind give into the topic today of learning and maybe optimizing learning?
Yeah, sure. So we're actually learning a lot about learning and like how human brains learn and things like that. Just to throw out some numbers, we all have about 100 billion neurons and 100 trillion synapses, the connections between neurons. And the very basis of our ability to learn is being able to modify or rewire the connections or synapses, right? So then a tantalizing possibility is, can we somehow optimize the process of rewiring synapses, rewiring the brain? Could we, for example, make synapses faster at learning, right? So believe it or not, neurobiologists have created many different types of mutant mice that make synapses actually faster. And they get mixed results. These mutant mice sometimes learn faster, so they're like these super mice, but sometimes at different tasks, they're dumber, basically. They learn much more slowly. And so we actually collaborated with a lab at Stanford that had some of these mutant mice, and we're trying to figure out why they sometimes learn faster or slower, right? And we came up with a theory that, even if you make the synapses change faster, right, you might imbalance the system so that some synapses become so strong that they're not available to become stronger, and then you can't learn anymore, right? So to test this theory, we devised another task, like a pre-training task, to undo that imbalance. So these same mutant mice that were quote unquote dumber at solving a certain task, if we gave them a certain experience that undid the imbalance of the synapses, they actually became smarter than the normal mouse. So that was the first time anyone had ever shown within the same subject, within the same mouse, modifying the genes to make synaptic plasticity faster could actually make the mice smarter or dumber depending on their previous experience. So your ability to learn, we kind of already know is a combination of nature and nurture. Your intrinsic propensity for learning is determined by biology and your previous experience. And here we could show conclusively by combining nature and nurture in different ways, we could make these mutant mice faster or dumber than wild type mice. So, there's a lot of work going on in the sector, like modifying our biology to improve learning. It's unclear whether we'll be able to do that in humans, but the principles that we learn from biological networks could eventually be applied to artificial networks. And we have sort of other work where we've used ideas from that work to make in artificial neural networks to enable them to learn multiple tasks without forgetting old tasks. So that's an example of transfer of information from neurobiology to machine learning. Yeah, so that's one example.
Yeah, I mean, that's so fascinating to me. And of course, based on all the different tweaks, life is just so interesting to me. It's always a balance. It's like you can't have too much of this. Like it's like too much of a good thing becomes a bad thing. And then, of course, too much of a bad thing is always a bad thing. But it's just fascinating that balance. So that must make that research a lot more difficult, because it's not like, you can just inject, it's not a binary thing, right? Okay, you just keep on going down here. So I'm curious to hear, as you're going through those experimentations, what are some of the biggest challenges that you're coming through, and also some of the key learnings that surprised you?
Yeah, I mean, for us, it was interesting to like devise the task that would enable these quote unquote dumb mutant mice to learn faster. I think like if these are ever to become practical devices, you'd have to do them in a much more reversible way. Like you can't mutate humans, of course, right? But you can imagine, just as we have brain-machine interfaces where you can help paralyzed patients to control a robotic arm to move. I mean, those are in place already in clinical departments. You could, for example, have learning prosthetics, right? That basically trigger biochemical changes in a very transient way when you want to learn. And people have imagined devices like that. For example, we tend to not learn everything. We only learn things that are interesting to us or might help us reap future rewards, right? So what happens is when we see a fact that we think might help us in the future, there's a little bit of a dopamine rush into our brain. So you could imagine sort of dopaminergic stimulation devices that you could press a button if you want to learn something and don't press it if you don't. And if you press it, you get a trigger of dopamine. That's not entirely far-fetched, because deep brain stimulation for Parkinson's disease targets the same system, right? I don't think we know enough to be able to give humans the power to trigger their learning systems at will. But it's not outside the realm of feasibility at the moment. So I think we're going to see examples of learning prosthetics operating in mice, relatively soon, right? Where the experimentalist controls the learning prosthetic device, not the mouse. But eventually we might want to transfer control to the mouse.
Yeah, no, I think that's so fascinating. I can't wait to see where that research goes. And actually, now that we're on the topic of learning, and you do a lot of research on neural networks, and seeing, actually teaching neural networks how to learn and seeing how they learn on their own. So what have you seen? Who learns better, neural networks or humans?
Yeah, that's a really interesting question, right? So we're bombarded with success stories of neural networks from industry and industrial labs, right? Like speech recognition, machine translation, playing games like Go. And they're very impressive systems. We've made a lot of progress there, but they're very, very different from humans. Like one of the biggest metrics along which they're different is the amount of data that they need. They're super data hungry, right? So for example, the initial attempt at Go that beat the world grandmaster, it actually played about 30 million games. It practiced in 30 million games. So if a human were to play 30 million games, they'd have to play about 120 games a day for 30 years, right? So it has a lot more experience than a human. Speech recognition systems, they're trained on simultaneous speech and transcribed speech. So it's like supervised learning. And they're trained in about 11,000 hours of data. So that's, for example, if you were to read and hear if you were to hear somebody read for 8 hours a day, you'd have to do that for 4 years to get, that amount of data. And like question answering, the training sets are sort of news articles, about 220,000 news articles. So to read that much, you'd have to read for you'd have to read 10 articles a day for for many, many years to do that, right? Actually for 60 years. So anyway, they're super data hungry, and humans are much, much better at learning with very little data. So what we do is we create much more structured representations of the neural networks create. And so there's research, we've done some of that research too, along the lines of trying to learn with less data, right? So, and especially label data, because that's super expensive to get, right? Where label data is where you for example, in image classification, you get an image and you get the right answer, like this is a dog, this is a cat. So somebody has to create those labels, right? So can we learn with unlabeled data? And so unsupervised learning is related to that. And people have made a lot of progress on that using a very simple idea, which is, oftentimes you get multiple views of the same object, right? Or even if you get an object, you can, like an image or something, you can crop the image and get different subsets of it, right? So you can kind of destroy the images in different ways and feed the destroyed image to a neural network. The neural network knows that it's always different views or destructions of the same image. So what it can try to do is can try to map all of those destructed views of the same image closer to each other in their internal representations, and then take different images and map them further away. So that's like that principle, surprisingly, is actually quite good at learning representations of images that are really useful for subsequent tasks, right? So now if you have this powerful representation trained on using unsupervised learning on unlabeled data, you just get a few examples of, say, a classification task, and it can do really well, right? So, and interestingly enough, our brain kind of does that, right? What our brain does, even in the retina, the first steps of visual processing, it parcellates the world into 20 different channels, right? And these channels are different aspects of the natural scene, like, grayscale structure in your rods, color in your cones, and there's 19 other kind of channels or so. You could imagine that these channels come together in their brain. They're kind of different destructive views of your world, and they try to piece it together. And as a result, they learn higher level representations that are useful for detecting objects. So, for example, machine learning people have followed this cue. They've done this task called colorization, where you take a color image, you turn it into grayscale, and you try to predict the color image from the grayscale. And they've shown that that actually segments pixels in such a way that they're useful for downstream object segmentation tasks. But our brain could do that immediately one step beyond the retina, for example. So I think this idea of trying to destroy the world and reconstruct it in interesting, like you have to destroy the world in interesting ways and then try to reconstruct it. That principle may have been found by evolution, like billions of years ago. And it's being found by machine learning people right now. So I'm very hopeful about that. And by the way, like all the amazing work on neural language models are basically that, right? You're trying to predict the next word or predict masked words in sentences. And then you learn really interesting natural language representations that can solve interesting natural language processing tasks. So I think that will be a very interesting growth area going forward.
I just want to dive into so many of what you said in detail. It's absolutely fascinating. But I also acknowledge that, I do want to get to the Q&A. So I'm going to ask you two more questions. Specifically, since again, by the way, I would encourage everyone to go to Professor Surya Ganguly's website, read about some of the research and the papers, and also, engage, with Professor Ganguli in other arenas. But I do want to kind of, since we're on the topic of learning again, kind of pivot the conversation a little bit. And so, given that, you have mentioned that neural networks don't really learn well, do you think they can help humans? Or rather, I should say, they don't learn this as quickly as humans do, given the limited amount of data. Can they help humans learn?
Yeah, definitely. So there's a lot of applications of AI to education, right? We've actually done some of that with the lead author was Chris Peak. We actually collaborated with Khan Academy, where we had a data set of sort of 50,000 students, kindergarten to high school, solving about 1.4 million math problems, right? So we had a data set, we had like the history of every student, right? Like, this is the math problem they got, did they get it right or not? And how long did it take them, right? So the question
Not every one of them solving 1.4 million math problems,
no,
right?
yeah, in total, yeah, some solved a lot,
wow.
some solved a small number. But in aggregate, we had this really large, relatively large data set, right? So we said, well, can we model the student learning process, right? Can we predict, based on the history of students' answers to previous math questions, whether or not they'll solve any particular math question well, right? So the way we did it is we trained a neural network to take as input the history of the student, the history of any student's questions and answers, and then predict the next answer, right? It was a big recurrent neural network. So what it does is you feed it in the history of what the student has done, and it creates an internal representation or a vector for each student, right? And that vector or internal representation is enough to predict the student's answer to any question, right? And our network worked better than any previous method at the time. And but what was cool about it is you could analyze what the neural network learned. So now each student gets placed in a point in the hidden activity space of the neural network, right? And different directions correspond to different skills that the student knows. For example, if the student is pushed in a certain direction, in internal space of the neural network, then maybe it knows fractions. In another direction, it knows like algebra, right? And so we could interpret like the different dimensions of skills. Then we could discover the prerequisite structure of mathematics from the learned neural network. So basically you could ask, if I pushed a student in this direction to acquire a certain skill, what other problems would the student be able to solve, right? And then we could discover, like, if you know fractions, what else will you be able to do? And we could create a little knowledge graph. And we discovered in a data-driven way the prerequisite structure of mathematics, right? So then the next step is like using the neural network. Like once you can model something, you can control it, right? So I mean, in a certain like very clinical perspective, learning is a control process. You want to control what's going on in students' brains by feeding them information and testing through feedback what they've learned. And based on that feedback, provide new information. But basically that feedback could be the student's skill levels, and we could optimize the next problem to give them in order to maximally achieve the next skill rapidly and accurately, right? So it's kind of based on the framework of model predictive control and control theory and things like that. So anyway, that's one example. Chris Peak has gone on to do other great work on, for example, automatic coding, automatic grading of coding assignments, right? There are these large MOOCs where people are creating lots of code and TAs are providing feedback. So you have this huge data set of student code and TA provided feedback. So can you just learn in a supervised manner AI systems that could generate interesting feedback to coding people in an automatic way, right? So, and that's relatively, I mean, it's tough, but it's doable because code is so structured, right? So that's another example. We're going to see lots of examples where AI is going to help in education, basically.
Yeah, and that, that sounds like we're going toward a path of more and more personalized learning. So let's say that, I mean, I've never been great at E&M, which is why I didn't go down the physics path, and now I've been reading a lot more physics books. But just to then, when it picks up that, for instance, I'm better at more math, and then it can kind of give me more of those to help me like really, go after the interests that I'm interested in, but then at the same time, understand where I might be struggling within the skill set of at least introductory E&M, electromagnetism, and then help me in guiding along to help me get much better at those skills. I think that's fascinating because I think, there's probably been lots of research saying that we do all learn differently. Certainly, like at the very base level, there's some more visual learners versus more, more text learners, I guess, for lack of a better word. But this could be a huge revolution. And I know it's already starting, but I'm so curious to see, where that goes toward.
Yeah, I think personalized learning is made much more easy because once you have models of the entire population of students, you can cluster students into different skill sets and then deliver personalized assignments for students in different clusters, right? And more importantly, you can learn what the clusters are, right? We've never had a data-driven window into the learning process as we do now because of online courses and things like that. So it won't just be educators making up stuff. It'll be a data-driven analysis of the learning process, which I think is super exciting.
Yeah, or like just a standardized, the curriculum, which may or may not work for some people. I mean, we know that. So I think that's fascinating. Now, in terms of, I read recently, and as we were talking, I know that you're now part of the Human-Centered AI Initiative at Stanford, and you're an associate director there. So that's exciting. I know, for MIT, we also have the Schwarzman College of Computing, which we'll hear from the dean later. But I know that, you're not thinking only about AI for education, but how we should educate the next generation of AI technologists and humanists and all students across the university. So how are you thinking about that?
Yeah, so at this Human-Centered AI Initiative that I'm helping with, we're actually trying to bring in the humanistic side of inquiry, the social sciences, the policy side of inquiry much earlier on into the education of technologists, right? Because AI is intersecting society in so many multifaceted ways. It's trying to solve all these problems in education. It might be creating other problems in the future of work and so forth. That it's if technologists aren't thinking about ethics and implications for society from the outset, from the very beginning of the genesis of the new technologies they're going to create. And we kind of missed the ball, right? So, and we and many others are bringing all of these ideas in very early on into the undergraduate education system, into the graduate education system. For example, I taught a class with a venture capitalist, Hemant Taneja, on entrepreneurship, AI entrepreneurship in society for the 21st century.
Another MIT alum, I believe.
Another MIT alum, exactly. 2 MIT alums teaching at Stanford. So yeah, we brought in people from many sectors of society. And we, more often than not, we weren't discussing the technology per se. We were discussing, for the most part, implications of that technology in society, how we can make sure the impact of this technology will be for the better and not for the worse. And so these things are inextricably intertwined. So we're creating sort of seed grants and research programs and so forth that really force economists and social scientists and philosophers and ethicists to work with CS people and medical people and so forth to really bring all of this stuff together.
Yeah, no, I think that's fascinating, and I think very important for us to discuss as well. I did have a few questions come in. I don't know if we'll get to all of them, but certainly I want to try to get to as many of them as I can. So one of the questions is, the first question that came in is, how do we prevent, quote unquote, politicized learning?
How do we prevent politicized learning? That's a really interesting question. There have been the short answer is I don't know. I mean, there have been situations where I've seen apps, for example, an app called Unbubbling, where, social media is, of course, creating a balkanization of society where you can end up in an echo chamber, right? So can you sort of pair up people from different echo chambers and have them talk to each other? So first, learning what the echo chambers are, bringing people together who would be susceptible to thoughts from the other echo chambers and have them come together and work together. Could we, for example, do that, right? At the very least, we could try to measure the degree of politicization and bubbling, and people are doing that on various
or I guess just in general bias, right? Any type of bias is what, I think what they mean by politicized is just the more of the biased learning based on, one school of thought or,
Yeah. I mean, honestly, I'm not sure, I think the onus is on humans to work on that. In companies, I mean, they're falling over themselves trying to figure out how to automatically detect hate speech and so forth and things like that, right? So it's going to be a long road. I mean, bias is sort of one step removed from hate speech and things like that, right? Or I mean, many steps removed from hate speech, but people are focusing on those types of problems at the moment. I haven't actually heard of anyone working specifically to remove bias because bias is one person's bias is another. I mean, everybody has opinions, right? It's hard to remove opinions from education.
But yeah, and I think it's also wonderful that there are many different experts from different fields that will come in and talk about these things. So I think just that alone and having those conversations and involving more people is wonderful.
Yeah. Ensuring a diversity of ideas. Yeah.
Mm-hmm. And then there's another question that came in from Anonymous that's, specifically to the learning side. So I think it really boils down to how can we make sure that the algorithm don't start to limit the potential of the students? I think this will be our last question, because I know we're almost at time.
That's a great question. I mean, for example, the application to education, there's sort of, in giving the next question to a student, you can have a range of difficulties, right? So there's this well-known thing of exploration, exploitation, and reinforcement learning, where you exploit what you know in order to reap rewards, but maybe you're not sure what you know about the students. You also explore. So negotiating this trade-off between exploitation, exploration, and delivering curriculum to students, I think, is essential to limit, this issue of AIs limiting students. But again, students can always seek to challenge themselves, right? So I think providing, the way I want to think about it is sort of a collaboration between the AI and the student, where the student is given some power over their own learning process. So if they're not feeling challenged, they can turn a knob on the AI system and say, hey, I want more, right? I think this notion of collaboration between artificial and human intelligence is something that will be very important going forward.
Thank you,
I just want to say thank you so much, Professor, for your wonderful insights. There's so much more to go on, and I encourage everyone to explore all these areas on your own, together with all the other AI resources that you may have.
Thank you, Surya and Wendi, for your
Thanks,
time.
Wendi.
It looks like we had a lot of insightful questions from the audience. And remember, you can always continue the discussion on the MITCNC Slack channel. If you're joining us for the next session, Competing in the Age of AI, that will start in 5 minutes.